and welcome to this month's episode of Future Cities. Today we will be discussing how cities prepare for an uncertain climate future. Your hosts this week are myself, Alicia Helmrich, and my colleagues Ray Lee and Geneva Gray. We are all graduate fellows, part of the Urban Resilience to Extreme Sustainability Research Network, or UREX for short. UREX is a network of researchers that focuses on integrating social, ecological, and technical systems to support urban infrastructure decisions in the face of climatic uncertainty. This is Alicia, and I am a PhD student at Arizona State University studying how engineers can approach infrastructure design for resilience when faced with uncertainty. Primarily, my work has focused on climate non-stationarity and extreme events. While my work has focused on water, power, and transportation infrastructure, I am most familiar with the water sector.
Hi, I'm Rayleigh, a civil engineer doing a PhD study at Arizona State University. My study is about the vulnerability of transportation infrastructures to extreme events such as wildfire and post-fire hazards. I'm also doing research on heat exposure of pedestrians and cyclists when they use the transportation system during extreme hot days.
Hello, this is Geneva, and I'm a climate adaptation scientist pursuing a PhD in atmospheric sciences at North Carolina State University. I analyze high-impact weather events and how extreme precipitation that occurs today will change under future climate conditions. Okay, I have a question for the engineers on the pod.
All right.
Where does rainwater go when it falls on a city? I can imagine where rainwater goes when it falls on a forest or farmland, like soil acts like a sponge for rainwater. But what happens when rain falls on concrete?
As rain falls on a city, it flows across all the hard surfaces we have built, such as rooftops and roads. So instead of creating rivers across our infrastructure, there's a system of drainage pipes, culverts, gutters, and storm sewers funneling that water off the streets. Sometimes there's even green infrastructure, allowing for those processes you recognize, Geneva. One of our guests today, Dr. Marissa Matsler, is studying green infrastructure with the Cary Institute of Ecosystem Studies, which runs a long-term ecological research station in Baltimore, Maryland. They are focused on many different things, looking at ecology from diverse perspectives, but one of their projects is looking at urban ecology in the city with a focus on social ecological systems. Hello, Dr. Matsler. Could you tell us a bit about yourself?
My name is Marissa Matsler. I am a social scientist, but I have had a very interdisciplinary career path so far. So I started in biology, molecular biology, and moved into environmental management, urban ecology, and then finally my PhD was in urban studies.
It's great to have a diverse background. In your research on green infrastructure, how do you see planners address rainfall?
A lot of that is driven from regulation around stormwater management. So I've seen a lot of the climate modeling conversation come in when we start talking about design storms.
So infrastructure is designed to a design storm.
Yes, a design storm is a rainstorm event that a building or road is designed to withstand. These design storms are determined from historical rainfall events to keep the streets safe and the city operable during the storm event.
I see. Engineers use our recorded climate history to design infrastructure like roads, culverts, and bridges to accommodate historically observed precipitation totals.
That's right. They use intensity, duration, frequency curves to get rainfall intensity, the quantity of rainfall, with the corresponding duration, that means how long the rainfall lasts, and the frequency of the occurrence.
Well, the climate is changing, so the frequency and magnitude of these extreme events seen in the past will likely increase. Can this infrastructure adapt to these increases in extreme rainfall?
It depends. Can you, as a climate modeler, give us an exact amount on how extreme rainfall events will increase?
I can give you a range. How it will change depends a lot on factors such as future of greenhouse gas emissions, the large-scale changes in land use, and the changes in global circulation, to name a few.
Well, that leads us right into today's topic. Today's episode is going to explore the uncertainties engineers face in infrastructure design practice, with a focus on climate change. We are diving deep into the problems and decisions that engineers confront in the face of an uncertain future. Let's take a moment to explore a real case study.
In the highway hydraulic design practice, State's Department of Transportation's design with 10 to 50 years design stamp and use a 100-year design stamp to check if the major drainage system could withstand a bigger event, while the current design stamp value engineers used are estimated 40 to 50 years ago with the assumption that the rainfall amount would not change over time. They fail to consider the changing precipitation norms and climate change effects. For example, according to NOAA, 100-year rainfall amounts for 24 hours estimation around the Houston area increased from 13 inches to 18 inches. That means a previously classified as 100-year events are now become a much more frequent 25-year events. And from the climate change models, we know that the future climate will be wetter. We just don't have an exact measure of how much wetter that future will be. Our infrastructures designed today based on the historical estimated IDFs may already be outdated when construction finished. What are engineers' strategy with this future climate uncertainty? I had the pleasure to talk to one of the practitioners from Portland Water Bureau, Kavita Hein, to discuss about this future uncertainty and how they cope with the uncertainty in their practice. Hello, Kavita. Could you introduce yourself to the audience?
My name is Kavita Hein. I'm the Climate Program Manager at the Portland Water Bureau, which is the drinking water agency in Portland, Oregon. And my role is to help our utility plan for and prepare for climate change impacts to the water system. So I work with many different staff across our agency to think about how we plan for climate impacts in our operations, our long-term water supply planning, and our daily maintenance and construction and other activities. I also work and collaborate with climate scientists and other water utilities with the Water Utility Climate Alliance so that we can learn how to adapt and plan for climate change and new methods that we need to be thinking about as we face this future uncertainty.
How is the Portland Water Bureau designing infrastructure for climate uncertainty?
We are thinking about planning for climate change, but one thing that we have discovered over the last 20 years that we've been planning for climate change is that there's a lot of spread in what climate models tell us about the future. They give us a sense of generally what could change, but they're not clear on how sort of the global or regional impacts will translate at the local watershed or water system scale. So that's one of the biggest sources of uncertainty in the field that I work in, because we're really trying to understand what are the implications at a very specific level and what do we need to do about that. So for example, we have a sense that climate change is going to shift the hydrology of our watershed, that is our primary surface water supply, which is called the Bull Run watershed. But we don't know exactly what the magnitude and frequency of drought years looks like, for example. Could we experience many years of drought in a row, or will it still be sort of an infrequent occurrence? So that's something we're really trying to investigate, both with climate modeling, but also really trying to understand the sensitivity and vulnerability of our system and what types of changes it responds to more than others. We're also uncertain about how robust and resilient our infrastructure will be in a changing climate. For example, will our infrastructure systems be able to deal with multiple future conditions or only a few? Will we be able to address flood events and drought events at the same time? Can our infrastructure deal with extreme heat waves and that type of thing? So really, at a high level, it's about how these global complex changes will unfold at the local scale that matters to us and to our ability to provide water to our customers.
The Portland Water Bureau is already experiencing the impacts of a climate that changes more rapidly than the built infrastructure of a city. The climate is changing, and the way we are designing infrastructure is not adapting quickly enough. As mentioned, infrastructure design assumes a stationary climate, using the past as a predictor of the future, but this assumption can be costly and lead to catastrophic failures. Typically, engineers implement fail-safe designs. Engineers will strengthen a design to withstand whatever is believed to be the worst-case scenario.
With this engineering perspective on uncertainty, really getting those tolerances down and thinking about the statistics to make sure that people are safe. So I think that has been, and that's been the way that things have been going, for at least 100 years in the United States with urban planning.
Yet not all disciplines view uncertainty the same way. Dr. Matsler further elaborates on how bringing diverse perspectives to planning can help create more resilient ideas.
there are a lot of roadblocks and barriers that city departments face when they're trying to work collaboratively. So I work with parks and rec departments and water utilities and transportation departments at the local level and see, how they're interacting or how they're collaborating to design primarily green infrastructure projects, but a lot of different infrastructure projects in the city. Since I'm often looking across silos, trying to see how people across different departments and these different disciplinary silos are working together, I often think that can lead to better solutions. And I think a lot of that is because when I was thinking about uncertainty, I was thinking that the more you work across these silos, the more you can probably lower the uncertainty of the outcome because you have all these different perspectives at work. So even from your own discipline, you may be able to, you may be missing something. There may be a gap in your work. So for myself, coming from the social sciences, I'm very focused on people, looking at who wins and who loses in the social system. But then, it's wonderful to be able to work with engineers who are looking at some of the physical aspects of a site, and they're able to address different gaps than I am. And so I think you can overall lower the uncertainty within a decision-making process by working collaboratively across sectors.
Kavita at the Portland Water Bureau is no stranger to integrating uncertainty into infrastructure design. In fact, her department has a very proactive way of addressing it.
At sort of the big picture level, we are, using climate model projections to understand, okay, these are some big changes that could happen to our system. And we have downscaled those climate models, but as I said before, there's still a lot of spread or uncertainty. And so we can't use the climate models to predict what the future will look like. Instead, we need them to inform how we think about the future. So to plan for climate change, we're taking an adaptive planning and scenario planning approach. And the key to this is to, instead of predicting the future, is to plan for multiple futures. So that basically means we want to consider a wide range of future outcomes for our system around climate change, but also around other important factors like what will happen with population growth and water demand and the economy in the region. We want to be prepared for a lot of different possibilities. So for infrastructure design specifically, the water sector, I think, needs to be thinking more about taking a very sort of modular approach when designing infrastructure. That means building, let's say you're an engineer, you have to build a certain piece of infrastructure, thinking about how to incorporate a way to build, expand capacity in the future so you don't have to build everything all at once. The goal is really to preserve options. So if you have to build some sort of treatment plant or some sort of facility, can you build it small enough where you can expand it in the future if you need to increase your treatment capacity? Or can you expand its ability to deal with flooding events and sedimentation? So really thinking very modular about how you go about building infrastructure and scaling up if you need to. And then also, I think engineers need to think about not stranding assets. So that's related to what I just talked about. You don't want to build something that is only going to work under one future condition where maybe you have, only droughts but no floods. You want to think about infrastructure and assets that do well under multiple different conditions, and that's what I was calling robust infrastructure. And then you really want to be flexible in your planning and design. So for us, the way that's taking shape is we are doing a 50-year water supply plan, and we are taking this adaptive planning approach. We're planning for 4 different future scenarios, and we're going to monitor how conditions unfold over time. So at regular intervals, every few years, we'll be regularly monitoring how are climate conditions unfolding, how is population growth and water demand changing, so that we can then decide at the time what are the best infrastructure investments, so that we're not overinvesting or underinvesting in an area when the future is going to look very different.
This adaptive management strategy sounds like a lot of work, and listeners may be wondering why climate science can't just narrow down the information people like Kavita need to provide services to the city.
Where do climate models fall into this? Well, these models are constantly evolving to create more informative data for those responsible for designing the future. These models run on computers that push the limits of what is computationally feasible. As computing power increases, the climate models get better. Climate researchers are also pushing the bounds of scientific inquiry. As we find more advanced and accurate ways to represent climate systems, we reduce the amount of uncertainty associated with model design. I spoke with Dr. Kenneth Kunkel at North Carolina State University about climate models.
I'm Kenneth Kunkel, a research professor with the Department of Marine, Earth, and Atmospheric Sciences at North Carolina State University. I'm also lead scientist for assessments with the North Carolina Institute of Climate Studies.
So what does a warmer world mean for extreme precipitation?
Well, very simply, one of the primary effects of increasing greenhouse gases is to increase temperature because of the imbalance of radiation forcing in the atmosphere, or radiative balance. And that part of that warming is warming the surface waters of the oceans. So the oceans are gradually accumulating heat because of this imbalance. They gradually warm. One of the fundamental principles of atmospheric physics is that the saturation water vapor pressure of the atmosphere is a very strong function of temperature, increasing by 3.5% per degree Fahrenheit. As the oceans warm, the atmosphere above the oceans becomes moister, and that in turn provides fuel for precipitation systems over land. Extreme precipitation, the source of water vapor for extreme precipitation events is invariably oceanic in nature. And so as this air is drawn into the systems, it's moister and can produce more rainfall.
Makes sense. So is there any uncertainty in that sort of relationship?
Well, there always are some uncertainties in these relationships. There is no essential uncertainty in the relationship of saturation water vapor pressure and temperature. And as the oceans warm, the air right next to the ocean surface will reach near saturation. And so the air right above the ocean surface will become warmer. Now, there's two major factors in extreme precipitation events that determine how much rain or precipitation falls. One is how much water vapor you have access to. And the second is what is the strength of the weather system that's causing the rainfall, or essentially what's causing the upward vertical motion in the atmosphere. That second factor, there is uncertainty about that. Will systems become stronger, or will they get weaker? Will they become more frequent? Will they become less frequent? Those factors, or sort of the weather system factor, can potentially modulate the changes in extreme precipitation from the increase in water vapor. And so that's an area of research that I'm currently pursuing.
Yeah, so I guess broadly, could you define uncertainty as it applies to climate change?
You mean how does it apply?
Yeah, how does it apply? Like what, when climate modelers say that there's uncertainty with, in the context of their models, what do they mean when they say that?
Yeah, there's several dimensions of uncertainty. What can we say about the future? What will the future be like in 2030, 2040, 2050? Well, one aspect of that uncertainty is what will society do in terms of emissions of greenhouse gases? Will we follow the current trends and continue to increase at the current rates, or even accelerate those rates? Or will the steps that are being taken to move from a carbon-based sort of energy system producer to energy sources that are non-carbon based, if that happens more rapidly, then the future trends in greenhouse gas concentrations will be less, and that will affect what the changes will be. The second factor is how sensitive is the climate system to increases. If we were to double, for instance, CO2 concentrations, how much warmer would the world become? That's an area that models are designed, the climate models are designed to, in part, to address that question. How sensitive is the climate system? The climate modelers produce or construct their models using different assumptions or a range of assumptions in doing that in terms of how to represent the physics of the atmosphere. The different choices actually produce quite a range of sensitivities in terms of how much warming we can expect. And so there is, the climate modelers are attempting to reduce that uncertainty, but it has been consistently maybe a factor of 2 to 3 going back 20 or 30 years. And that range of sensitivities of the climate system or estimates from the climate models has not decreased very much over the decades.
So when there's that range of uncertainty, how do climate models communicate that, climate modelers communicate that uncertainty with folks who are in charge of designing infrastructure and, city engineers?
Don't know that I can answer that very credibly.
We have other people who...
I can talk about how I tend to address it.
Yeah, that's good.
I'm not a core climate modeler, but I'm using modeling results. And, several approaches I've used in terms of communicating that. One of the essentially facts that I emphasize is that there is uncertainty about, for instance, how much warming might occur, and there's always uncertainty about the choices that human society will make. But there's only one direction that these changes are going in. That means that the traditional way of estimating future risk based on historical data is a really bad choice. And so the first kind of step is to convince the designers and engineers that yes, there is uncertainty, but we do know the direction of change. We do know that the risk of extreme precipitation events will increase. We know that the risk of higher temperatures will increase. Even if one were to use something simple such as extrapolation of trends, current trends or historical trends, that would be better than the current approach of using just historical data to estimate future risk.
Climate models are just a piece of the uncertainty puzzle when it comes to constructing resilient infrastructure. Kavita tells us how climate models are useful in her work.
Climate models are very important tools that they do give us a picture of what the future could look like, and we can test different questions and assumptions about the system. We can understand the sensitivity of our water system to, for example, change in temperature or change in evapotranspiration or change in precipitation. So we can test those types of questions out with climate models. One way we have used climate models is we've downscaled them to our watershed, which is, again, the Bull Run watershed, and we've done some reservoir water supply modeling where we've projected a range of different reservoir storage outcomes depending on what happens with these climate models. And then we are also working on a research project with a local university here in Portland called Portland State University, where we are mapping historical and future storm events and trying to understand how climate change will shift the type of storm events that we've experienced in the past. So we're working with other researchers to understand how we can use climate models, not just from downscaling, but looking at sort of large-scale weather patterns. We've also worked with many other universities to develop a hydrologic model in-house that we're using regularly in-house. So these tools are really important, I think, for the water sector so that water utilities like the Portland Water Bureau can, again, test the sensitivity of our system and understand under which different conditions do we see more stress on the system.
To recap, climate models are used to provide multiple realizations of how the climate system may respond to higher average and extreme temperatures. Using multiple models that incorporate the different energy and emission paths provide a range of possible outcomes. City planners use those results to plan how future climates impact the future of their cities. Now, let's consider adding a few more complex factors.
As has been alluded to, infrastructure uncertainty is not only stemming from climate change. Infrastructure is a social, ecological, and technological issue. A few listeners may recall the SATS Infrastructure podcast from May 2019, which dove into this topic with Dr. Samuel Markov. In our interview, Dr. Marissa Matsler also elaborated on some of the social and political issues surrounding infrastructure uncertainty.
Now, as we start to look at climate change as well as other ongoing issues within our country, a lot of the social issues, a lot of the political issues, we realize that some of these, the way that we've narrowed in has actually left a lot of people behind.
Yes.
And so while some groups of people have very certain and predictable lives, they're getting the services they need, there are aspects of our population that are not being served. And so we're needing to integrate across these sectors and actually bring in, I think, a lot of the people side to this. So looking at questions of systemic racism, looking at issues of misogyny, a lot of these things that seem to be really far away from the field of engineering, like on the surface, are actually, it's really important to look at how those decisions were made in that very narrow disciplinary space to make sure that everyone is being served. So I think looking at that, like looking at infrastructure as this process through time that continually impacts people's lives, is something that I've tried to do and try to, again, I think the main take home point for me is this like collaboration and working across these different sectors to really make sure that we're serving everyone in the city.
Uncertainty is not just an issue for engineers, but something every single one of us must consider in our daily lives. We asked each of our guests today to think about how uncertainty impacts their lives outside of work. First, Kavita explores what uncertainty means for the next generation.
Oregon and in Portland, we have great access to the outdoors and nature, so there's a lot of opportunities to enjoy our natural area, and it's something I love doing with my family. And one thing that I really am uncertain and worried about is thinking about what will Oregon look like and feel like in the future in a warmer climate. What will the seasons feel like? What will being out in nature feel like? Will I be able to go out as often if there's a lot of smoke or if it's too hot? And what will the communities feel like? Will people still live and work in the same way that they do? So I do think a lot about that. And in particular, I think about it because I'm a mother. So my daughter's 3.5 years old, and I worry and I'm very uncertain about what her future will look like. Will she be able to experience the same things that I experienced when I was younger here? And if not, what will that mean? Will she be in a world which is very different from the one we're in now? And we're already seeing changes, right? So those are the types of things that I think about that kind of keep me up at night.
When posing the same question to Dr. Matsler, she discussed the privilege she's had to make it to where she is today.
And I think that everybody in their daily lives are dealing with uncertainties on so many levels. And being able to reflect on this question, I really just thought about how lucky and privileged that I have been throughout my life to have my needs met very consistently. So not having uncertainty around food, shelter, family, like that has been very consistent throughout my life, very stable. And so I think it's important to acknowledge in our work, that my actions and my research and how I approach the world has really been shaped by the fact that I've had this consistency, and so I can take risks in different places in my life. For example, like getting a PhD and becoming an academic. I can do that because I don't have uncertainty in other aspects of my life. On a personal note, I was also recently diagnosed with an autoimmune disease, which has really given me this new appreciation for uncertainty, because my body will react rather unpredictably, or not as it has in the past. And so that's just been getting used to a new rhythm and sort of understanding. I think what the real lesson for me in this uncertainty was that, and how it's applicable to my work, is that to recognize everything around us as this process. I think I was saying a bit earlier as well, but this idea that this is like helping me recognize infrastructure as a process, just as my body is like constantly changing and degrading and adjusting, infrastructure and everything around us are in these same processes. And I think that when we design policy, we have to account for this fact that things are changing and are in flux. And often, when I think about how I grew up and like with so much consistency, it's often easy to overlook that and to kind of think of things in stable state. Like once we put something in the ground, it will be there like that in the future. And so I think this is a really good question to reflect on all these different things in our personal lives that allow us to see the world in different ways, and that we can bring different research questions and different ideas to this process of design in the city, to make sure that all of the needs are being met for all the different populations in the city.
Finally, Dr. Kunkel.
Probably the sources of optimism one source is that there does seem to be some shifting of national opinion about the reality of climate change. It's not where I would like it to be, but it seems to be trending in the right direction. And so the possibility for taking adaptive measures, at least, I think have increased. I've seen more, what's the word? More acceptance of the need to do something from some of the organizations that play a role in that.
The number of considerations city designers and engineers must account for sounds daunting. Luckily, collaboration between climate scientists, engineers, policymakers, community leaders, sociologists, emergency managers, and residents brings diverse and exciting ideas to the table to solve climate resilience problems. I hope this podcast helped shed some light on the complexity of this problem. It may be complex, but experts and communities from all backgrounds are coming together to approach the future uncertainty in a way that creates resilient future cities.
Thank you for listening to this month's episode of the Future Cities podcast. This week's hosts were Geneva Gray,
Rayleigh,
and Alicia Homerick.
Special thanks to Kavita Hein, Marissa Matsler, and Kenneth Kunkel. Please tune in next month for another episode of Future Cities. Take it easy, folks, and we'll leave you with this haiku.
Uncertainty plagues cities with tenacious change. Optimism prevails.
The Future Cities podcast is an outreach effort brought to you by the Urban Resilience to Extremes Sustainability Research Network, or UREX as we usually refer to it. To learn more about UREX, visit www.sustainability.asu.edu/urban resilience. If you have any questions, feedback, or suggestions for future episodes, you can email us at futurecitiespodcast@gmail.com or find us on Twitter at FutureCitiesPod. If you enjoyed the episode, please rate and subscribe to us wherever you get your podcasts. See you next time.